So for starters, like what's it say? So 4 to any number plus 2, would it be divisible by 3? So should we check that it actually works? You're saying no, we shouldn't check it works. It doesn't work. Why? Well, I mean, it says n is greater than or equal to 0. So should we start with n is 0? So what happens when n is 0? You get 4 to the 0 plus 2, which is 1 plus 2, which is 3. So wouldn't we say, well, yep, that is divisible? Yeah. All right, what about when n is 1? We get 4 to the 1 plus 2, we get 6. Well, that works. When we get n is 2, we get 4 squared plus 2, 16, 17, 18. All good. N is 3. What's 4 cubed? 64 plus 2, 66. So exactly. So at what point do we go, well, if I've done it for enough n's, is that going to work? What about if n is 10? Maybe it doesn't work for when it's double digits. How would we know and prove definitively if it works for all positive values of n, including 0? So in order to do that, we have this process called mathematical induction. And we're going to start with looking at proving that things are divisible by certain numbers. You can use induction to prove the sum of various numbers. So back to when we did sequences and series. We've got those statements where, 1 plus 2 squared plus 3 squared plus 4 squared equals the sum of blah, 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 blah. We're going to prove that that is true rather than just going, okay. We're going to use products. We're going to involve matrices and even trigonometry. And a thing called factorials that you might not have seen. Yeah, it involves everything. And this is an awesome topic that really solidifies and improves your algebra skills. The first topic of year 12 next year is induction. We basically do it here. And then next year it's like 1 week, but then it's embedded in a lot of topics that we do. So it's great. And it's got a set process. And if you know that process, I don't know why I'm recording this. If you know that process, then it's just the same thing over and over again. So your notation and how you write stuff down is very, very important. Okay. So we're ruling up. 1 margin, today's date, induction, divisibility. So what I've got on the left-hand side, and there's one last thing to put, but in the yellow, this is what we have to have every single time, right? If you don't include any of these, and really I'll put that one in the bracket, you need to put the original statement, right? Your PN statement. So you must put this, and this is we're talking for tests. When you're doing it in your book, obviously good to have nice habits and routines, but it's like, if you can get, just the first bit you can get down, don't write all the yellow bits yet because we might need space. It's like your, what's it called? First principles, right? Got to make sure you put the limits, got to make sure you put f dash of x equals and all that sort of stuff. You've got to put the process correctly. I'll explain it as we go. So we're starting with the first bit. You've got your statement. You're all writing that down. That's beautiful. We are proving P naught. So like we just did before, we're going to say P to the 0 plus 2 equals 1 plus 2 equals 3. And I've already not left enough space. So we just write. And we must then write, therefore, P naught is true. And I'll just stop for a minute. Okay, so what we were saying with the section before, we were just going 0, 1, 2, 3, and we're proving it works for every single time. What we are going to do is, it's called the domino method. What we're going to do is we're going to say, can we prove that this thing would be true for any value of n, whether it be the first 4 values or somewhere in the middle? And if we can say, well, if it's true for this one, let that be k. And if we can say it's then also true for the next one, right? Well, then it would have to be true for the one after that, because then if we've proved it was true for this one and the next one, well, what if this was then that first one? Then it's true for the next one. Does that make sense? And it's true for the next one, the next one, the next one. And because we've proved that it's true for the very first one, that means it has to be true for all of them. Does that make sense? So what we're saying here is we're going to go, right, we're going to say any value for n, like that's why we call it k now, not n. Just introduce another letter to be. We're going to assume that's true. If we assume that's true and we can prove that therefore the very next statement would be true, that means all the consecutive ones would then have to be true, and because we've proved the first one, well, that means it's true from the first. All right, so how do we write this down? Assume pk is true. Well, what we're going to say is that we're going to assume 4 to the k plus 2 equals, how do we say that something then is divisible? And keep your hats on here, folks, but lo and behold, we're introducing another, oh my God, another letter, right? And we have to say where a is an integer. And I hope you realise that makes sense. If we're saying that, go back again, so sorry if you're copying it down, but this was true because this was then going to be, this was 2 times 3, this was 6. I should do it the other way around really, shouldn't I? This was 3 times 2, this was 3 times 6, this was 3 times 22, but all of these have to be integers. If it wasn't an integer, if it was like 3 times 1.5, that's not divisible by 3, right? So all we're saying is if this equals 3 times a whole number, that means that thing there has to be divisible by 3. Got it? Right, so you must have written this statement, assume pk is true. Must. And now we're actually going to prove it. How are we going to prove it? And leave just a little bit of a line here, a gap. Leave a little bit of a gap because you'll see in a minute. I like to do this. You'll see your textbook is a little bit different, but this works for me. So pk plus 1, we go 4 to the k plus 1 plus 2. And what you're going to try and do is you have to use pk, right? Because that's what we're doing. We're going to prove this by assuming that's true, and we're hopefully going to show that it equals 3 times something, 3 times an integer. Yes? So here we go. How on earth are we meant to use this? Now we've got options. I could replace the 2 with 3a take 4k, couldn't I? And that's possible. It will work, but what I like to do is I like to replace and use this 4k bit here, 4 to the k. How are we going to do that? So this is 4 to the k equals 3a take 2. This is using your method stuff. How can I substitute this 4 to the k in here? Can you separate this? How can you separate it? Isn't that 4 times 4 to the k plus 2? Would you agree? Yeah. Same statements? So this now becomes 4 times, but what is 4 to the k? 3a minus 2. Are we happy with that? I'll stop in a minute to let you digest. And again, I'm pulling out the yellow pen here, using pk. If my Adams family were here, what would they ask? Do I have to write that? Yes, you must. That is part of the process. Normally what we do is we give someone in the class the job that they always have to remind me. Using pk, because I sometimes forget. Oscar, I think I'm going to give you that crown. And then sometimes we just write Oscar instead of using pk. All right, here we go. Do you need a moment to digest that? Okay, let you read it. I'm going to try and prove that this thing here can be written as 3 times something. Okay, so the first thing that we can do is we're going to expand the brackets. Big tip, you're going to have some things soon that will go, instead of divisible by 3, it might be they're divisible by 17, divisible by 28, whatever. So don't bother. I mean, I know you can all go 4 times 3 is 12, but in this case, I would actually say just leave it as, because that is our common factor that we want to pull out anyway. So imagine if it was dividing by 17, that would be 17 times A. I don't want to times that by big values. I just can't be stuffed. Anyway, 4 times 2 is minus 8. We get plus 2. I hope a lot of you are already smiling. Why? Just because you're happy, but also because you can see, yep, this is 4 times 3A minus 6. So I can quite easily now pull out that common factor of 3. So I get 4A minus 2, right? And because this is an integer, and why is it an integer? Because A is an integer, and you're timesing everything else by, yeah? So, oops, get my yellow. Therefore, PK plus 1 is true. And this we must finish off. Once again, I've got Matthew's voice in my head over here, but we must write the statement, the final statement that ties it all together, and we will say since, or as, whatever. You had the textbook, you can copy it from the textbook in a minute. So since, what did we start with? No, didn't we start with since P of 0 was true? So since P of 0 is true, and what did we then do? Right, but we proved, good, we proved PK plus 1 was true whenever true PK was true. So since P0 is true, and P of K plus 1, oops, is true whenever PK is true, then Pn is true for all n greater than or equal to z. Oops, no. Yeah, wait. I got a what from the class. By PMI. So that is just summing up everything. The whole thing was we had to prove Pn was true. So 4 to the n plus 2 was divisible by 3. Have we done that? Well, I think we did. Because we proved that P0, the first value for n, was true. And then we proved that for any K plus 1, so it could be P5. We proved P5 was true. But then we also proved that that would only be true when P4 was true. That's what that's saying. So PK plus 1 is true whenever PK is true, the one before it. Then all Pn is true for that by, what does you think PMI stands for? Proof by mathematical induction. I get my... It's a saying, people. Oh, order dash. All right, so I've summarised a fair bit there. We're going to dive straight in. This was the example that we did. Hello? We're not doing the binomial expansion bit. We're just doing the proof by mathematical induction, even though the binomial is beautiful. So we can have a look over here. I said is an integer and A is greater than, they said is greater than or equal to 1. All right, well, and here's our statement. Notice I'm saying P of 0. That's just because my habit from when I was doing it, and P of K with the brackets, but there, right? So by all means, go and have a look-see. But we are going to dive straight in. I sort of want to do a harder one, but no. We're doing 1 and 2, but shall we just start with, okay, we'll start with 1, yes? It's pretty similar. Let's go. All right, so we're writing our statement. So Pn, we are saying 3 to the n plus 1 is divisible by 2. They could have also gone, prove that that is always going to be even. Ollie, are you with us?
Yes.
Pen in hand, please. Let's go. All right, we start with, it's got n is greater than or equal to 0. Now, do be careful. Sometimes it can be n is greater than or equal to 3, or n is greater than or equal to 1. So if it was greater than or equal to 1, then you start with P of 1, not P of 0. In this case, you have to do 0 because that is your first term. So we'll go, that means we've got 3 to the 0 plus 1. That's 1 plus 1, which is 2. Therefore, P of 0 is true. Do you understand now why you have to write that P of 0 as true? Because it's in our final statement. If you didn't write it, then it doesn't sort of flow. All right, we must say we are assuming PK is true. Okay, this now becomes 3 to the k plus 1 equals 2a. And I'm saying a is an integer. We've got that. We want to prove. I leave a bit of a gap because, as I said, I always use my 3 to the k. So I basically rewrite that, and I have 3 to the k equals 2a minus 1. So we want to prove p to the k plus 1 is true. And when we're saying is true, we are saying we want to prove that it is divisible by 2. Yeah, Tom?
In the original statement, do we need to say n is an integer because it says for all integers?
It's getting excited. I didn't put it's an integer. Thank you, Tom. Okay, so we come back down here and we've got 3 now. Wherever the k is, we're going to replace it with k plus 1. Plus 1 equals, and now we're going to do our thing. So the tip is when we're doing these, split your indices. So 3 to the k plus 1, we know that that is now 3 times 3 to the k plus 1. What are we going to do? All right, we're going to now say this is 3 times, but we've got up here using pk, that is going to be 2a minus 1 plus 1. Oscar's going to yell out. So we must write using pk, curly brackets, whatever. Okay, 3 times 2a. Again, if you wrote 6, that's okay. I'm actually concentrating to write 3 times instead of just 6. Okay, so now we've got 3 times 2a. Minus 3 plus 1 is minus 2. Lo and behold, that means I can now pull out my common factor of 2. That is an integer. Therefore, pk plus 1. Then you've stuffed up, or it's not true. Sorry, the question was if that is not an integer. So if that was like a 3a take a half, no good. All right, now, what I used to do maybe after next lesson, over here we can go ish. Anyone know what ish stands for? Insert statement here. Correct. But because we want to get into the habit, we are going to write our statement this time. All right, so what did we start with? We started with since. Right, since P naught. And look, you've got your help sheets. You can write them down. You don't ever have to, you know, memorize it. But if you're realizing it is just you restating the process you followed, I think that helps. So since P naught is true, and we prove that PK plus 1, correct, is true whenever, you can write whenever, shorten it down, when PK is true, then that allows us to say that then Pn must be true, or say is true, for n greater than 0. Huzzah. All right, next page, we're done. We're jumping to 3. So once again, you're getting into the routine, and what happens is you probably, especially when we get to those longer ones, the sums and the products, you will write, I don't know, 4, 5 lines, and technically you haven't really done any maths, you're just rewriting stuff. Anyway, so Pn, we are now going n cubed plus 2n is divisible by 3. All positive integers, so I can say that's where I go, boom, with the little plus up there. Okay, positive integers, so we're going with P1. So we would go 1 cubed plus 2 times 1 equals 3. Therefore, P of 1 is true. All right, we're into the groove. What did we then go with? Right, assume so we end up with k cubed plus 2k equals 3a. Yep, where a is any integer. To prove. Now, I leave that little gap because I put that thing in there. If you want to do it to the side, you don't have to leave the gap, you know. So, to prove k plus 1 is true. So, what do? Wherever k is, we have to replace it with k plus 1. Agreed? Uh-oh. So, k plus 1 cubed plus 2 times k plus 1. And we want to try and prove that that's got a common factor of 3. Now, why did I just say uh-oh? Uh-oh, 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 uh-oh. Because I have to expand this. But this just makes me love this topic even more. Because to expand it, instead of going, oh, k plus 1 squared times k plus 1 and do the whole thing, I can use my best mate, Pascal! Pascal! Oh, I see some blank faces there. Oh, see again. See? You never use... Oh, my goodness. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4. I mean, I could have stopped because all I need is that row there. But I'm going to show you because this is helpful. And we did this in... Yes. So, why is this helpful to us? Because if I wanted to expand right? If I wanted to expand, and I'm going big time here, if I wanted to expand a plus b cubed, what this means is it's going to be 1 times a cubed plus 3 times, now it's a squared, times b to the 1 plus 3 times a times b to the 2 plus 1 times b cubed. Now notice, add your powers. 3, 2 plus 1, 3, 1 plus 2, 3, 3. Right? If I wanted to expand a plus b to the, let's go to the 5, what would it be? 1 times a to the 5 plus 5a to the 4b plus a to the 3b squared right? So when I was just needing you guys to expand k plus 1 cubed, right? I don't have to do, let's work out k plus 1 squared and times it by, I can just go, that's going to be 1k cubed plus 3k squared times 1, which is just itself, plus 3k squared times, times 1, 3k times 1 squared, and 1 squared is just 1, plus 1 cubed, which is 1. So you can do it, boom, really quickly. And you're going to get a lot of these little tips and tricks. We even deal with fractions within this unit. So even if you're not carrying on with spec next year, this is just a great topic to enhance your basic algebra skills. Anyway, so this now becomes k cubed plus 3k squared plus 3k plus 1. 2 times k is 2k. 2 times 1 is 2. If you also have messy writing, this is a great topic to make sure that you tidy it up. Right, what are we going to do? What do you mean put it together? I'm actually going to now replace my k cubed with this. So k cubed will now be 3a, take 2k. So 3a minus 2k plus 3k squared plus 3k. And what are we hoping that's going to happen? Hopefully you're going to pull out a 3 from somewhere. We've got 3a. Now I'm going to go, there's only of 3k squared. That's nice. Minus 2k plus 2k. Yeah? Plus 3k. 1 plus 2 is 3. We're laughing. Yes? We've got a common factor. Oops. Well, I was actually waiting. I was waiting for the end to go, yay, oh, fantastic. Have we actually got full marks for this? And we haven't put over here using, Oscar, you didn't call out, using PK. Why we have to write it is because we're showing, remember the whole point is we assumed PK was true, and we're proving that PK plus 1 is true using PK. So if we haven't actually used it, the statement at the end doesn't hold true. Yeah. Okay, that's an integer, therefore PK plus 1 is true. And just for today, we're writing ish.
Yes. Can we do that in place?
Going Pn, boom. I'm going P, what is it that we're doing for Pn? Positive integers. So P1, is it true? 1 times 1 plus 5. True? Yes? All right. So we actually just want to get to the maths for this bit, because our lesson is nearly done, and this is a nice one. So assume PK. True. We are assuming K squared plus 5 equals 6A. 6A is an integer. Do we want to expand that?
Yeah.
Well, okay, you said no, but then, all right, assume, maybe not, we'll see. Assume P of K plus 1. Oops, what am I doing? Getting so excited to prove. Okay, so we're trying to prove K plus 1 times K plus 1 squared plus 5. We want to try and say that that's going to be, what is it? Equals 6 times something. Okay, so we're looking at this and we're going, what can I replace with at the moment? Not a whole lot of stuff. Do we have to expand? Yes. So here we go. K plus 1. Now this is where, if you're a good mathematician, you are saving yourself some time and energy, because we should be able to go K plus 1 squared is? Excellent. So that's going to be K squared plus 2K and plus 1 plus the 5. So I've got plus 6. Agreed? If you're still dallying with, oh, how do I expand K plus 1 squared? You're slowing yourself down. Do we agree?
Yeah.
Right. Next line.
Wouldn't it be easier just to times K plus 1 through first and then do K cubed?
Oh, that's even better. So, yep, could you go K plus 1 cubed plus 5, K plus 1? Like it? You do? Okay. Pardon? Whichever way you go. What haven't we done yet? We haven't used PK, right? So up here, that's not in a very nice form. So now we probably will have to say that's K cubed plus 5K equals 6A. So can I replace the K cubed? Yep. So now I've got, yeah, baby, I've got my 6A take 5K. Plus 3K squared. Oh, I said squared, I wrote cubed. Sorry, the bell's about to go, so we're going quick, but I do want to finish this. We're going, yeah, no worries. What happened last time was we had the 6A, we tidied up, we've got the 3K squared, minus 5 plus 8 is plus 3, plus 6. And we were able to then pull out the common factor and we go, oh yeah. No. We wanted to prove it was divisible by 6, and yet this is not that. So, this happens like once in a blue moon. But please notice, I'm going to keep my 6A out the front because that is divisible by 6. That's done and dusted. This bit here, yes, I can pull out 3. And I get K squared plus K, plus 2. I've done something wrong somewhere. Oh, did you all get that? Sorry. Include your 6 here. Pull out your 6. You pull out your 3, k squared plus k. Thank you. The noise outside distracts me. Right, we've got 3. I can now pull out k, and I have k plus 1. I probably should have done that the next thing. Now, what I can say is this is divisible by 6. Anyone know why? You're going to... Because, look at this. This is k, and then k plus 1. So it's a number, and then the very next number. Agreed? Now, you give me any number. 5. The next number is going to be 6, right? Isn't one of them even? So an even number times 3 is going to have to be divisible by 6, right? If you started with an even number, yeah. So this, you could just say that bit there is even, therefore the whole thing is divisible by 6. Sorry, we ran out of time. The bell's just gone. But yes. Homework.